Hello students, I am Dr. Sreemoyee Biswas and I am here to take you through different topics of data structure and algorithms. I am also currently teaching this subject in the ongoing semester and I am making these videos on the repeated requests of my students. And I am picking up the first topic for explanation here as the sorting algorithms. It means that if we are given a list of elements, say stored in an array, how we can arrange it in a sorted manner. Sorted manner can be either in ascending or descending. So during the following lectures, we will see the details of bubble sort algorithm, followed by insertion sort algorithm, followed by selection sort algorithm. And the last two algorithms in this list are merge sort and quick sort. I have written this down for a quick glance that merge sort algorithm and quick sort algorithm both follow divide and conquer approach. I'll also tell you about all these algorithms in detail, so stay tuned for my next videos. Hello students, in today's lecture we will look into the algorithm of bubble sort and we'll see how we can sort a given list of elements using this algorithm, what strategy it follows. And next we'll look into the time complexity of this algorithm both in the best and the worst case. So please stay tuned with me for the next part of the video. Thank you.
So to understand bubble sort, let's assume that we have an array of size 5 and name A. It is an integer array, and say we have stored the following elements into the array, and on the top of them with red mark I have written the indices of the respective elements. So now let's understand what does bubble sort say. Bubble sort says that we should first compare these two elements, and since we want to sort the array in increasing order, okay, this is also important that here we are sorting the array in increasing order. Okay, so since we want to sort the array in increasing order, therefore the left index should be a smaller value when compared to the right index, correct? So it says that if A of I is greater than A of I plus 1. This is opposite of the condition that we actually want. So if it is like that, then a swap must be performed between A of I and A of I plus 1. So see, what are we saying here? That if the left element is greater than the right element. So if this is my I, if this is my I index, then this is my I plus 1. So now A of I is 20 here. A of I plus 1 is 25 here. Obviously, I have initialized I with 0. This is pseudo code. This is not exact code. Okay. So this condition does not satisfy here in this particular case. So if it doesn't satisfy, then we do nothing. But if this condition gets satisfied, then we must perform a swap. So for the first iteration, for the first comparison, this condition does not satisfy. So we are doing nothing. So after checking this condition and then taking the decision whether we want to perform the swap or not, after that, so whatever the decision is, so whatever the result of if is, upon that it is only decided whether the swapping will be done or not. So only this is the body of if here. But whatever the condition evaluates true, whether this condition is true or this condition evaluates as false, irrespective of that, after this I plus plus must be performed. because once we have checked the relation between these two elements, next I would want to check the relation between these two elements. So let's see now. The value of I is 1. So after this is performed, I becomes 1 from 0. So now I'll compare A of 1 and A of 2. So A of 1 is 25 and A of 2 is 6. So now with these values, this particular condition gets satisfied. So as it will get satisfied, we are going to perform the swap. So what are we swapping here? We are changing the value of these two elements that we have compared. So simply you can say, see, so after first comparison, the array remained unchanged. But after the second comparison, now my array looks like this. Okay, so we have basically compared A of 0 with A of 1. Then we did not perform a swap, it wasn't required back then. Then A of 1 and A of 2, and we had to perform a swap, and after this the condition is this, correct? Now we are going to check this condition with the next two elements, because now I have, see, even after the swap is done, I plus will take place. So when it happens, so now my I will be, so now my I is 2. So the comparison will be done between A of 2 and A of 3. So what is the value of A of 2? It is this. If I write down the indices like this, so A of 2 is 25 and A of 3 is 12. So as per this, again this particular condition gets satisfied. As soon as this condition gets satisfied, the swapping will take place. So now what we can say is, here the swapping, if I tell you that the swapping will take place, then how the array will now look like? It will look like this, correct? Now after this, the swapping is done, we'll increment the value of I. So now the value of I is 3. So if I is 3, means I is here, it's pointing here. So I plus 1 is this, correct? So now we are going to perform comparison between A of 3 and A of 4. So now my A of 3 is 25 and A of 4 is 5. So we are going to do a comparison between these two elements, and since the condition here gets satisfied, we are going to perform a swap. So now as soon as I perform a swap, see what happens here is 5 and 25, both their values get swapped. So this is the array that we'll get after we have traversed all the elements once. Okay, so you can see that 25 was the largest element of this array. Can you verify this from the initial condition of the array? Yes. So we can say that after we have run this particular algorithm once, the largest element here gets bubbled up to the largest index. Okay, that's why the name bubble sort is given to this particular algorithm. Okay, so this is done only once till now. So all these are termed as pass 1. Okay, so we can say that, or after, now how many comparisons have we done? If n equals to 5, that is the size of the array, then how many comparisons were being done? 1, 2, 3 and 4. 4 comparisons we have done. So we can say that after n minus 1 comparisons, the largest element gets its proper place. And this was the first pass, pass 1. Correct? Now let's see after this pass what will happen. So after this pass, now my array is like this: 26, 12, 5 and 25. Now carefully see how we perform the comparisons. So again we are going to start from index I equals to 0 after the first pass. So we compare these two elements, we see that 20 is greater than 6. So we are going to perform a swap. So now my array will become like this. Everybody agrees till here? Okay. After this, the swap will be performed between these two elements. Again, there is a need to swap the elements. Correct? After this is done, we are going to compare these two elements. We again find that swapping must be done in this case also. Correct? After this, these two elements are being compared, and again they full. Now just tell me one thing here. After this comparison, what happened? See, let's forget about this particular comparison. Okay, so these two elements got compared and there was a swap of the values. After this, can you observe that now 20 gets its correct position? 20 being the second largest element has acquired the correct position, has acquired the position where it should be in a sorted array. Okay, so now what we can say is, okay, now tell me, how many comparisons have we made? So it's 1, 2 and 3. So now we can see now it is evident from here that 25 has already got its correct position. And now since 20 is also placed, do we need to perform a comparison here? Do we need to perform this comparison? No, this comparison is not needed. So what we can say here is that in pass 2, only n minus 2 comparisons are needed to place the second largest element at the correct position. Okay. So following this same trend that we observed in pass 1 and pass 2, can we say this, that after pass 3, the third largest element will be placed at the correct position? Can we say this? Yes. And how many comparisons will it require now? Only n minus 3. Because see, if you look at the current position of this array, now only 2 comparisons will be made. These 2. Because 25 and 20 are already at their correct position. So we are not going to revisit this particular position, this. Instead, we are only going to perform the comparisons here. So after pass 4, carefully look at this. What will happen? The fourth largest element will get correctly placed in a sorted array. Yes? Okay. How many comparisons will it require? N minus 4. So my n is 5 here. So only one comparison. How? Because after pass 3, okay, if I draw the array, okay, after pass 3, my array will now start looking like this. I hope this is clear to you why it will be looking like this. Because the third largest element, which is 12 here, is correctly placed here. So now this part is already sorted and arranged in the required order. So only comparisons that will be required will be in this place. So in this place only one comparison will be performed, which is n minus 4. N is 5 here. So only one comparison will be done. And as soon as this comparison is done, you will swap the values to get 5 here and 6 here. Now tell me one thing, after this do we require a pass? We do not require a pass, because after this, after pass 4, we are saying that the fourth largest element is placed at the correct position. So now only one element will be left, and one element is already placed at the correct position. Hence we can say that for an array to sort an array of size n, n minus 1 number of passes will be required when we are using bubble sort, obviously. And within each pass, how many comparisons will be required? That we have already discussed here. Okay. In pass 1, n minus 1 comparisons. In pass 2, n minus 2 comparisons. In pass 3, it will be n minus 3 comparisons. Okay. So I hope bubble sort algorithm is clear to you. Let's quickly discuss about its time complexity. Now what is the best case? The best case here would be that you already have a sorted array. Say your array looks like this. This is an already sorted array. So what will happen in this case? You compare this. So first of all we run pass 1. In pass 1 first you will compare these two elements. No swap. Then you compare these two elements. No swap. Then we will compare these two elements. No swap required. Then we will compare these two elements. No swap required. So in pass 1 what we will see that no swaps are required. Correct? So if we modify our code, our pseudocode in a way that if in any pass, it can be any of the passes, okay, if in any pass no swaps are taking place, then in general we can say that now the array is sorted. This will imply that the array is correctly sorted. Once it is correctly sorted, do we need to perform other passes? No. So this is going to be the stopping criteria. Stopping criteria of the algorithm, that no swaps are required. So if we have an array which is already sorted, then only one pass will run and then we'll detect that no swaps are required. So when only one pass is running, what will be my time complexity? It will be big O of n. So in best case, bubble sort will take big O of n time. What is the best case? That the array is already sorted. Now looking at the worst case. Worst case or average case, we have already seen that 2 loops will be required. It's easy to understand. 2 loops will be required. If 2 loops are required, they are running within each other, then the time complexity is always big O of n square. Correct? One loop will run for the passes, that is n minus 1 times, and the other loop will run for number of comparisons within the passes. Correct? Worst case will be the array is reverse sorted. So what will happen? You compare these two, there will be a swap. Then you will compare these two, there will be a swap. Then you compare these two, there will be a swap. Again you compare these two, there will be a swap. So after pass 1, what will happen? The array will look like this. The array will look like this after pass 1. Then you will compare these two, again swap. You compare these two, again swap. You compare these two, again swap. So in this way, both the loops will have to run to their full capacity to get the sorted array. Therefore, we see that the time complexity in the worst case will be big O of n square. Thank you.